So parameterizing the plane, we're going to go u, v, and then z is going to be f of u comma v. So we put the function in. Yeah?
Could you move the little kind of arrow?
The thing that's hiding that important number?
Yeah.
So our disk down in the xy plane is x squared plus y squared equals 16. All right. So parameterize the plane. We need to get a normal vector for the plane. Two ways to do it. We've seen that with planes, we could put it in the traditional general form and look at the coefficients. Or we can use RU cross RV. It's not going to matter. Watch and see that we get the same thing. So with this parameterization, R sub u is 1, 0, 0. R sub v is 0, 1, negative 1. Cross them and we get 0, 1, 1. That's the same thing that we would get if we rewrote this plane in standard form. We would have 0x plus 1y plus 1z equals 6. So those coefficients, 0, 1, 1, right there. And so that's kind of what we've been seeing regularly. So if you're dealing with the plane, you can definitely use that shortcut. Put it in general form and pull off the coefficients. Now the curl of the function. So curl of the function, 2, 1, 0. If we take this function and we do the determinant, I won't go through all that. I think we actually did do that last Thursday, or Wednesday. So that will be our curl function. And then we are good to start evaluating. So the one side of Stokes' theorem is a double integral. That's the surface integral. So let's do that first. So the double integral is going to be the double integral of the normal component of the curl. So that's curl of f dot n throughout the surface. And whatever we call this surface, I forget if he calls it S or something else. Doesn't matter. Yeah?
So we did do this problem in the 14.7 notes, right?
Yeah.
Okay. Just want to make sure I'm not.
Yep, nope. We did it right at the very end. This is just 14.7. I slightly rewrote it, though. So this is going to be the double integral of curl f dot n. So what do we get here? Curl f dot n. That simplifies to what? Curl f dot n? 1. So this is going to be 1 dA over r. And so...
Isn't it S?
Well, this term, when we evaluate, when we have a field and we dot it with n, it turns into a dA. It turns into a dA when we replace this n. Like the ds, remember, is equal to the length of n times dA, and this n is a unit normal, and it's n over the length of n, and they cancel. Do you want me to write that?
Sure.
So remember that when we do our evaluation, this becomes curl of f, and we can think of this little n is supposed to represent a unit normal, so we would write it like this. And again, I don't know why they don't use a capital N so that it would make more sense over here to write it as little n divided by the length of little n. So you just have to remember that this is a unit normal there. And then ds, when we convert that to dA, it's the length of n dA. And then this is over r. So these guys just cancel. So our evaluation just turns into curl dot n, but this is a little misleading, I think, because it'd be better to write this as a capital N, and then it would be curl dot small n dA. So it's the length of n's that are canceling when we do our conversion from ds to dA. And many calculus books use capital N to designate a unit normal, capital T to designate a unit tangent. This book doesn't do it in this particular case, which makes it a little bit confusing. Will?
So yeah, how do we get r in terms of t from the r in terms of u and v?
Oh, we're not there yet. We're doing the double integral. We'll talk about that in a minute when we do the single integral. So with the double integral, we use the u's and the v's because we have our surface. When we do the integral around the outside, that's when we have just t. But on the inside, we have u's and v's.
So first we parameterize f in terms of t, like we normally do.
Let's talk about the curve in a minute, though. Right now, we're doing the surface in terms of u's and v's. Okay.
I'm sorry.
So the surface is a two-dimensional surface, so it has to have two parameters, u and v. So Stokes' theorem says that the double integral throughout the surface, so those are u's and v's, that's going to equal the single integral around the outside.
Okay.
So we'll get to the t when we do the single integral around the outside.
All right.
Omar?
Not qualification.
Yeah.
Some word that starts with C. Clarification.
Clarification, okay.
Dumb clarification question. Is that cross product RU cross RV? Is that N?
Yes.
Okay.
Yep, that is n. That is n. That's right. RU cross RV is always n. Not necessarily capital N. Capital N, if we really should be thinking of capital N as a unit normal, this isn't necessarily a unit normal.
Right. Yeah, that's probably what tripped me up. I thought in was that your normal and you need R prime in order to do that.
Yeah, so when we get to t, we'll take R prime. So the funny thing here is that with the way that he uses the little n here, then you have curl f dot little n ds over s equals curl f dot n dA over r. And so it looks like something's missing. That's why I would prefer it if you wrote that as a capital N, just to distinguish when we're dealing with ds and when we're dealing with dA. Because this n right here is not normal, is not a unit vector, but this normal is a unit vector. Weird.
We would only use the capital N, so the unit normal, if we were using the arc length parameterization?
So if we were parametrizing the surface, but we're talking about a surface, so we don't really have an equivalent of arc length parameterization for a surface.
Okay, if we were using S's.
Yes, if we
Okay.
somehow we had S's here, which
Okay.
We did on like one.
not with capital S though, with little s.
Oh, yeah.
Yeah, so there's not really an analog that we could do. We aren't going to be able to parameterize our surface with respect to S. So it's more of a semantics thing. Okay, so there is our curl. There is our normal. When we dot the two together, we get 1. So that's going to be 1 dA over R. And that just gives us the area of the region R. And the area of R is pi r squared. And the radius down there, I think, is 4.
Yeah.
So we get 16 pi. So that should be our result.
And if we were to do this, say, on a test, we could just do this and say we found the double integral using the area because we know the area,
Yeah, using geometry.
using geometry. Okay. So that's kosher.
That's totally kosher. Super kosher. So now let's do it with the line integral. So with the line integral, now we have to parameterize just that curve, which is the boundary of that tilted ellipse. So we have to come up here and parameterize this boundary curve. And we have to parameterize it in a way that lines up with the normal vector's direction that we used for the surface integral. So this normal that we used for the surface integral is in the up direction because z is positive. So it's in the relative up direction. So we're going to go counterclockwise if we are looking down from the z-axis. We just have to make, which is our standard direction of parameterization. So right there, that guy is our parameterization if we were down in the xy plane. Circle of radius 4 centered at the origin. Everyone okay with that? Now we want to include the z component. So the z component is 6 minus y. So I think we can squeeze this over here. So the curve will have parameterization r of t equals 4 cosine t, 4 sine t, and then what will the z component be?
6 minus 4 sine t.
Exactly, 6 minus 4 sine t.
What?
And I think that's where there might have been a goof on Wednesday with that parameterization or something, or with the derivative of it.
I was plugging it into F.
Oh, plugging it in wrong. Okay. Okay, so there's our parameterization. Now, this side of Stokes' theorem is just a single integral and we are going to take our parameterization, plug it into our field correctly. So minus y is minus 4 sine t. And then the middle is negative x minus z. So negative x minus z, negative x minus z. I think that's the part that we were missing then. And then y minus x. So y minus x is 4 sine t minus 4 cosine t. And that's all going to get dotted with. What does that get dotted with? The derivative of this. So dot that with minus 4 sine t 4 cos t, comma minus 4 cos t. And that's dt. And that goes from 0 to 2 pi. Very circular. Very circular. So then we dot those two together and integrate from 0 to 2 pi.
There'll be some cancellation.
Yeah, there will be a bunch of cancellation.
And we get 16 pi. Right?
And we will get 16 pi. So should we dot that all out together? Or are you okay, dot that, there's some cancellation, integrate, and you'll get 16 pi. All right, so let's do a couple more of these because these are tricky. So let's go to the next one. So we have similar type of thing. We have this ellipse, and it's going to be contained in the plane z equals 1. All right, so we have a floating ellipse. And that's our vector field. So with Stokes' theorem, we always find curl when we want to do the surface integral. So Stokes' theorem is curl, and we're going to see in a moment when we get to the next section, the divergence theorem is going to be dealing with, flux is going to be dealing with divergence. Okay, so Stokes' theorem is going to be dealing with curl, divergence theorem is dealing with divergence or flux. So curl of this, you guys can do curl by now. So we just do the determinant and we get our curl vector field. Here is our surface, z equals 1. The normal is going to be 0, 0, 1. Several ways that you can get to that normal. One is the simple way. 0x plus 0y plus 1z, pull off the coefficient 0, 0, 1. Or you could parameterize that surface, and you'd get the same thing, 0, 0, 1. All right, so parameterizing a plane, same way, just to make sure, we won't go through all the details, but if you were to parameterize this plane, just z equals 1, what would the parameterization be? Parameterizing the plane.
0, 0, u.
0, so 0, 0, u is going to give you a line called the z-axis. Right? 0, 0, u, where u is unlimited, would just give you, all points would have an x and a y coordinate of 0. So that would just be the z-axis.
UV0?
What was that?
UV0?
UV1.
1.
1. UV1.
So close.
Yeah, very close.
Because then when you take,
So now you would do r sub u cross r sub v, and you would also get 0, 0, 1. So that will give you the same exact normal vector. It doesn't matter which way you go.
How do you know that?
So we want to get a whole plane,
Yeah,
a bunch of ordered triples. The z coordinates of every ordered triple are 1.
because we're the z-plane being at 1.
Yep. So all the z values are 1, but then we need a variable to represent all the possible x's and all the possible y's. So we just choose u and v.
Just throw it in there, just
Yep.
call it. Okay.
Right? Because we have it, whenever we parameterize a surface, we need 2 parameters. So in this case, u is representing, it's representing x, and y is represented by v.
And this only works for planes, correct?
Yep.
Okay.
Yeah, this technique would work for this. And I mean, more generally, if you think that this is a function, if that's a function, you would always do u, v, f of u, v.
Okay.
So in this case, if you think of this as a function, then that's why that's a 1. That's
Okay.
one way to think of it. Will?
Yeah, so, if I were to take, the parameterization and, get the more normal function. If we're two-dimensional, I take the derivative and swap the positions in two numbers and turn the new y coordinate negative.
Yes.
How do you do that in 3 dimensions?
We'll get there. We're not. That's in the next section.
Oh, okay.
Yeah, we'll get there. Definitely. That's flux.
Slow your roll, buddy. You'll get
So,
this soon.
yeah, that's flux. We'll get to that for sure. It's actually simpler in 3 dimensions.
All right, I've been having a hard time following classes lately, so.
Yeah. So it's so the idea with flux is that in 2 dimensions that's a little hard because we do that swip and we swap it and change the sign. In 3 dimensions, it's going to be easier. It's going to be way easier, actually. I'll check in with you when we get there. Okay, so double integral. Everyone agree that curl dot n is this?
Yeah.
Oh, yes. That's how you got that.
Obviously.
All right.
I was like,
All right. So should I write curl dot n? So curl of f dot n ds over the surface. So we are going to do curl dot n dA. So again, for that same kind of weirdness that they don't write that as a capital N, so it feels like we're skipping a step or something. So we get that. Now, the domain for this is down in the xy plane, and we have a z there, so we need to say, whoa, wait a minute. We can't have a z in there. We need to turn it into x's and y's, if there are x's and y's to replace it with. But what does z get replaced with?
1.
1.
So we get 1 minus 1.
So we get 1 minus 1, which is 0. All right. Okay, so that is using the double integral side of Stokes' theorem. Now, if we want to do it using the line integral side of Stokes' theorem, then we have to parameterize the curve, and then we do the dot with r prime thing. So let's try that. So the line integral side of Stokes' theorem, so that's this thing, the FDR. All right, so we parameterize our curve. So let's come over here and parameterize our curve. So our curve, the parameterization r of t is going to equal, how are we going to parameterize this ellipse?
We're going to use cosine and sines.
Absolutely.
I'm sorry, cosine theta or t.
How about that?
Can you explain the middle component? Yeah. Please.
R sine theta.
So we always use r cos theta and r sine
So
theta.
disappointed in us.
The denominator in front of the x's, denominator of x is 1. The denominator here is if you were to write it as a quantity squared, it's y over 2 quantity squared. So we'd have half as the r value.
It's y over. Oh, I.
So think about it this way. That one is it's a little more complex, perhaps. But let's check. If we squared this, we would get cosine squared of t plus 1/4 sine squared of t equals 1.
Yeah.
Right? And so that matches then, right? We get so we normally are thinking about x is equal to, for an ellipse, we would write x as a cosine theta and y or t, and this as b sine of t. So that will give us an ellipse. So we just look into the denominator and whatever those square roots are. So for example, if we had x squared over 4 plus y squared over 9 equals 1, what would the parameterization be?
We'd have 2 cosine t, 3 cosine.
Yeah.
I forgot about parentheses, and I thought that the equation was the quantity of x squared plus y squared all over 4 equals 1.
Yeah, that. Oh!
It's true.
Then you have a circle.
Yeah, see, that's what.
Then you would have 2 cosine t and 2 sine t if you were in a circle of radius 2.
Question.
Yeah.
So how come over there you did 1/2, but over here you did 2? Square root?
Oh, good question. Let's see. Did I do it right here?
No.
No. This should be 1/2 and this should be 1/3. Because when we solve for cosine here, cosine of t is going to be 2x and sine of t is going to be 3y. So we know that, or maybe I did it, well, one of them is wrong. So we know that sine squared plus cosine squared has to be 1. So which one is right and which one is wrong? Let's see. This, actually I had it right the first time. I have it wrong over there.
Damn it.
So it's wrong.
Dang it.
So it's wrong on the.
So let's see. Well, let's figure out exactly. I was not expecting to spend time on this, so I didn't think carefully about it. So here is the solution that we need, right? We need sine squared plus cosine squared is 1. So this squared plus this squared is 1. So let's come back over here and check. So this should be 2 and not 1/2 then, because let's write it all out just because there was a goof. All right.
Because there was a.
There was a goof. All right, so here let's just notice if x is cosine of t and y is 2 sine of t, then the idea is that we solve for cosine and sine, so this one gives us y over 2 is sine. And then we need cosine squared plus sine squared equals 1. So it should be that. Should be with a 2, not a 1/2. Sorry about that.
So what's the thing on the left then?
Which thing? So this is 2, because that's a square root of 4 is 2. And that's a 3, because square root of 9 is 3.
I'm not sure where the 2 and the 3 are coming from.
Here, this 2 and 3?
Yeah.
From this one. Square root of 4 and square root of 9.
Where's that coming from?
This is just a made-up problem.
Oh, no.
Yeah. So
This is just a made up.
this is just a made-up problem. So for example, if you had x squared over 16 plus y squared over 25 equals 1, it would be x equals and y equals
4.
4 cosine of t and 5 sine of t.
Yay. All right.
Yes, there we go.
Logic
There, okay, now we're done with that. Let's keep going. We don't have time to keep. Let's keep going. The algebra. Okay, so there's our parametrization. Now we plug our parametrization into our vector field.
Don't we need a balance first?
Oh, well, 0 to 2 pi, because it's an ellipse. Yep. So we plug our vector field, plug into our vector field. So we have negative, where's our vector field? Up here. Y is 2 sine of t, comma. Next component is x times z, so that's cosine t. Next component is minus y, so that's minus 2 sine of t. So there's our f. And then we dot it with r prime. So we take our parametrization and we take the dot. We are going to dot product it with the derivative. And the derivative here is minus sine t, 2 cosine t, and 0. So let's dot those together. We get minus 2 sine squared of t plus 2 cosine squared of t.
That's sad.
0 to 2 pi.
Oh, wait, I thought you said pi.
2 pi, because it's a full ellipse. So 0 to 2 pi will take us all the way around. And there should be a dt here. And what do we get when we integrate that? A couple ways we could do it.
You do
Yes, you're
cosine
doing it
2t?
0. That's true. So you could use power reduction identities, which work absolutely fine, or what else could you use?
2 cosine 2t.
Yes. So you know that cosine squared of t minus sine squared of t is cosine of 2t. So you could use that also.
And that's using those power reduction identities.
That you could prove that using the power reduction identities.
Because we did that one.
It's like
Yep.
sine a
You
plus
can
b,
prove that.
sine a minus b, cosine a plus b, cosine a minus b, all those.
Oh, the using
Is that where
the
that comes
sum
from?
that comes from the sum and difference identities.
Oh.
Yeah, the way you were talking about it was from the sum and difference identities. So yeah, this will all end up being 0. So you can either use power reduction or you could use double angle.
To what extent do you want us to work that out on an exam?
In more detail than this.
So if we said it was cosine 2t, it'd just integrate to sine.
Exactly. Does everyone follow that? because we have cosine squared minus sine squared, so you're going to have a cosine in there, and when you integrate, you get sine, and sine at those two endpoints will both be 0. Exactly.
Would you
So
not
that-
get a negative sign?
No, it would be a positive sign. Because it's cosine squared minus sine squared,
Right. which
and
is
then when you
positive.
integrate cosine, you get sine. You don't get minus sine.
But it wouldn't even matter, because it's gonna be 0 either, whether it's negative.
Okay, so that was both sides of Stokes' theorem there. Let's try both sides of Stokes' theorem for this thing. We've got a vector field, and we've got a curve. It's the boundary of this plane in the first octant. Boundary of the plane in the first octant. So this is one of those tetrahedron things that we've seen a whole bunch of this semester. So these are pretty easy to sketch. We would have, if we look at this, the z-intercept is 4. Oh, aren't all the intercepts 4?
Yeah.
They're all 4, right? Does everybody agree?
Is it still a tetrahedron?
Uh-huh.
It's just a more perfect.
It's just a more perfect tetrahedron. Yeah, so it's a tetrahedron where it's got, I mean, it's still not a perfect tetrahedron like you would be rolling in D&D, because these three sides each have a length of 4, but that side, it's still not totally perfect, I don't think, because all the faces would have to have the same area. And I don't think this tilted face has the same area as the 3 planar faces. We don't care about that. All right, so this is our curve. The blue thing is our curve. And that's the boundary of this plane in the first octant. Again, curl of this vector field, you know how to do that, determinant. Right, you can do that. That's a vector field. There's your curl. Now we need to figure out the normal vector for this tilted plane. Well, again, there's a few ways we could do it. We could parameterize the plane, u comma v comma f of uv, and then ru, rv, cross them. Or if you put the plane in general form, ax plus by plus cz equals d, pluck off the coefficients. That would also work. And then there's this third way, too, that works. Z sub x, z sub y, and plug it into this formula. This will always work also. This is a third method. If you have a function. If you have a function, we proved this earlier in the semester that this will always be normal to a surface that's given to you as a function. But it doesn't matter. There's 3 ways. Whichever way fits is easiest for you. If you're dealing with a plane, most of us would say, oh, this is the easiest way, is do that and pull off 1, 1, 1. Totally fine. Okay, so then we dot the curl with the normal vector, and we are going to get the double integral of curl dot that, curl dot n. And now this can be dA over r, and that r is down here in the xy plane. We're integrating on this domain. So that's what we're talking about by r.
So,
Question, Will?
no, I think I figured it out.
So we're going to dot this with this. Okay, now again, we have z's, but our domain is down in the xy plane. We can only have x's and y's for independent variables. The dA is a dx dy or dy dx. So we have to get rid of that z. We need it in terms of x's and y's if it's possible, and in this case, it's very possible. We have minus 4 multiplied by this. So we get minus 16 plus 4x plus 4y. And dy dx or dx dy? What do you want to do?
dy dx.
Say again?
dy dx.
dy dx. So if we do dy dx, then the x's are coming from the constant interval, and we're using an element that's going this way. If we had it drawn traditionally with just the xy plane, we'd call that a vertical element. So x's are going to go 0 to 4, and the y's are going to go 0 to
4?
That would be a rectangle then, or a square. If we were going 0 to 4, 0 to 4. So we have to figure out the equation of this line here. This line is going to be equal to
Minus x.
minus x plus 4. 4 minus
Did you
x.
say 4 minus x?
Yeah. Hum's back!
Hug's back.
All right, so then integrate this with respect to y and plug and chug. And the question is, do we want to integrate? Do we want to go through this
Nah.
mundane part? This is the hard part, is the setup. Integrate this with respect to y, plug in the 4 minus x, integrate that with respect to x, and plug in 0 and 4.
So I might have been writing down notes while this was
Mhm.
going on. Where the heck did you get 16 plus 4x plus 4y?
By multiplying this -4 times z, and z is equal to that. So z gets replaced with what it's equal to in terms of x's and y's, since our dA is a dx dy, or a dy dx.
Why is it the boundary of the plane in the first octant? Like, what is that?
Just because that's given.
But I mean, like, that seems kind of odd, I guess. Like, couldn't the boundary of it also be the boundary that keeps it from going into the 8th octant, as well as one
Sure.
that keeps it from going into the 2nd octant?
Yeah, they just chose this because it's easy to visualize. Like if somebody said, if somebody had it, so if this is, say, x and y, and this is down below the xy plane, if somebody said, you could certainly build a tilted plane that would create a tetrahedron below the xy plane, but it'd be really hard to visualize and draw. So they're trying to give us something that's simple enough for us to draw, and so they're saying, okay, we're going to take the intersection of the plane with the first octant.
So is it only that bottom part that you shaded in, or is it also the ones on the sides?
So the actual surface is this tilted triangle. That's the surface.
But
But the
C-
domain of the surface, so C, the curve going around the boundary, is just the blue curve. Okay. So it's not a full tetrahedron, it's just the face of the tetrahedron.
all of the faces of the tetrahedron, or
Nope.
just one?
Nope, just the one.
Where is that specified?
Right there. So it says the boundary of the plane in the first octant. So this triangle is the boundary of the plane in the first octant.
I get that, but why are we going with that bottom?
Because when you integrate a
Triangle.
surface, you look down into the domain. And so the domain for this surface is down in the xy plane,
Okay.
right? So if we wanted to, we could use the domain back here in the yz plane if we wanted to.
And it would get a
Get the
similar
same
result?
thing,
Okay.
same result. Or we could use the xz plane as the domain also.
All right.
So whenever we have a solid, we have to decide which plane we want to use as the domain plane. Now, once we're in chapter 14, 99% of the time, they give us surfaces where we just use the xy plane as the domain, almost every time. Because there's so many other things going on that they don't want us also to be thinking about, should we use the xz plane or the yz? So most of the time, there's going to be one or two that use a different plane. But
Okay.
so that was our choice there. So right here, as soon as we write dA, this is where we're choosing. So I said, let's get rid of the z and turn it into x's and y's because I'm assuming we want to go with the easiest method, which is using that.
Okay.
But we could turn this into a dy dz or a dx dz if we wanted to. Yeah, so it's totally up to us. We'll always go with dx dy or dy dx if possible, if that's the easiest way. So let's do the line integral then around that boundary curve. So that's this one, that's FDR, circulation. And we have to take our vector field and take our parametrization, plug it into the field, multiply by r prime. Now, I'm not going to work this one all the way out because there's 3 different things we would have to do. What are those 3 different things we would have to do?
Parameterize.
There's 3 curves that are stuck together, right? So that boundary is a piecewise smooth curve.
So you'd have to do each line.
We'd have to do each one. So we would have to parameterize. We would do this.
Like the triangle? Like
Yep.
the projection is what we would have to parameterize? It's not that bad. We could,
It's not the projection. It is the triangle itself.
like in the XY plane.
No,
No.
in the
Oh,
free
the,
space.
okay, I got you.
So we would have to parameterize from here to here. which you know how to do. It's a line segment, so we go on the interval 0 to 1. So all three of these would be 0 to 1, 0 to 1, 0 to 1. And we want to go counterclockwise, so we're going to go this direction. We need to go in a way that it lines up with this normal vector. That normal vector has a relative up direction, so we'd want to parameterize this direction around. So we would do terminal point minus initial point times t plus the initial point. Come to this one, terminal point minus initial point times t plus this initial point. Come to this one, terminal minus initial times t plus the initial. Take the derivative and line integral it out. So that would be the line integral way. Now in the test, it's going to say use the line integral method or use the double integral method, so you don't have to do both.
What if f wasn't dependent on z? Would you have to? Could you
So-
only get one of them?
So if the vector field didn't have a z in it,
Yeah.
so then what was the question?
Would you only have to do one of the faces?
One of these lines?
Yeah.
So when we do the line integral, we have to go around all three of these line segments. So we'd have to do all three no matter what the vector field looks like.
Okay.
So if we do the line integral method, we have to go around, we have to add up the line integral for each of those three, or we're going to do the double integral over the face. And when we do the double integral over the face, we're going to use the xy triangle as the domain triangle. All right, let's go to another one. All right, so here is the one example where we're not going to use the xy plane as the domain.
All right.
All right. So, first off, don't get tangled up in the notation here. This just means curl of f. And they tell us that we want to evaluate the line integral in Stokes' theorem to determine the value of the surface integral. Assume that n points in the upward direction. And we are dealing with this vector field. And that vector field is a radial vector field. So R is xyz. And then we do xyz divided by the magnitude of xyz. So this is what our vector field looks like in Cartesian coordinates right there. So that's our radial vector field in Cartesian coordinates. All right, so we always have to have a field in the surface. The surface is the paraboloid 9 minus y squared minus z squared. So this is a paraboloid that's opening into the board. The x-intercept is 9. All right, everyone okay with that? So when y and z are both 0, so when we're on the x-axis, we're out here at 9s. So all I'm doing is drawing the boundary of the paraboloid. So the paraboloid is opening into the board, but we're stopping at x equals 0. So x equals 9 is the vertex. And that paraboloid is opening into the board. So this is just like the upside down paraboloids that we've dealt with in the past. But usually when we deal with them, we're writing them this way, with z as the dependent variable. So this one is just opening backwards. Okay? But with Stokes' theorem, we don't care what the surface really looks like. We really only care about this boundary. So whether it's a paraboloid that has that boundary, or an half of an ellipsoid, or a cone, does not matter with Stokes' theorem. If we're going to evaluate the line integral in Stokes' theorem, the surface that generates that boundary does not matter. Could be a million different surfaces with the same boundary. Right? You can imagine a whole bunch of different cone or paraboloid or ellipsoid type things that all have that same boundary down there. The line integral will be identical for all of them. Does not matter what the surface is. So we are dealing with just this curve then. The surface does not even matter. This is the boundary of the curve. We have this open cup, an open paraboloid, and the boundary curve is just that circular ellipse that's right at the mouth of this paraboloid. Okay, so paraboloid 0 to 9, excluding the base. In other words, it's open. So the boundary curve is right here. we set x equal to 0 to get the boundary curve. So this is in the x, y, z space, but when we let x be 0, this circle is in the yz plane. So that's the equation of that circle. So we need to parameterize a circle of radius 3. So we have 3 cosine and 3 sine, but they're going to be in the y and z positions, and the x position will be 0. All the points on this circle have an x value of 0. So this would parameterize the curve in the yz plane. Take its derivative, and then to evaluate the field on our curve, we take the x, y, and z for the curve, plug it into the vector field, and we get this, and it simplifies to 0, cosine, sine. Simplifies tremendously. And then our evaluation, this actually I have a little typo here. There shouldn't be, we don't need the circle here. Right? The circle here is not, we don't need that circle around the integral there. As soon as we turn it to a dt, this is an a and a b, and we don't think about that circle thing there. So f dot r prime. So we take the simplified f, we take our r prime, and let's dot them together. And our interval is 0 to 2 pi because we had a circle. And when we dot those two together, it looks like we get minus 3 sine cosine plus 3 sine cosine. So that all is going to equal 0.
So uneventful.
So uneventful. These guys, this book, there's so many of these in the last 2 sections where it's like 0 again and again and again. I don't quite know why. The thing that's a bummer about that is that
If we get one on the exam that's not 0.
well, should I have at least one on the exam where there's a 0?
Yeah.
At least one?
Just tell us ahead of time so you can
Tell you.
Yeah, if you put 0 for all of them.
That would be great.
Yeah, exactly. You can probably get half of them right. All right, so 0 is the line integral piece. Now, if we wanted to do it the double integral piece method, this would be harder in this case because we have a piecewise smooth solid. We have the paraboloid, and we have the plane that it's intersecting, x equals 0. So we would have to do the surface integral on the paraboloid plus the surface integral on that base, on that disk, not circle, but disk. Everyone follow that?
This is excluding the base.
So no, well, but if we were going to use the surface integral side of Stokes' theorem, oh, it did say excluding the base. Sorry. Okay, I was thinking about 14.8. You're right, we don't need the base at all. In 14.8, we would have to include the base. 14.7, we're not including the base no matter what. You're right, thank you. So the surface is just the paraboloid. When we get into 14.8 and we treat it as a solid object, then we would have 2 surfaces that we would have to integrate on top of. But in this section with Stokes' theorem, we don't have to do that. So good call. So how would we parameterize this paraboloid?
Just do the regular.
Do ours.
Yeah.
So we would do, let's at least write the parameterization down of the paraboloid because that's such an important skill is to parameterize. That's always the hardest part. So the paraboloid.
I minus r squared.
So we're going to have r of uv equals, and not too hard though, right? So the x component is going to be the simplest, right? The x component is just going to be 9 minus whatever we choose for those other things. All right, so
So can we do 9 minus u squared minus v squared and then do u for y and v for z?
this is not a great way to parameterize it.
Okay.
Because, so you could do it this way, but then you're going to end up with, when you set your intervals, they're not going to be constant intervals because your cross sections are all disks. So we want to try to think of it in terms of disks. Each cross-section is a disk. So what if we did something like this? So for this paraboloid, what if we did, so if we think about the relationship between the radius of the disk and the height of the paraboloid, or the distance from the YZ plane, can we come up with a relationship there? So if we think about this as 9 minus r squared, x equals 9 minus r squared. So x equals 9 minus r squared. Then the r, let's see if we can come up with a relationship between r and x.
9 minus.
So that's going to be 9 minus x. So r is going to be the square root of 9 minus x. So the x coordinate is sort of the free variable. The x is going from 0 to 9. X is going 0 to 9. So let's do it this way. So what we could do is say, let's let this be u. And that's just going to go 0 to 9. And if that goes 0 to 9, then can't we do square root of 9 minus u times cosine v, comma 9 minus u square root sine v? Will that work?
You had me right up to cosine and sine.
Yeah.
So cosine and sine take us around a circle. So r cosine theta, r sine theta.
Okay.
But we have an r that's modified based on this relationship. So it's kind of like when we go to spherical coordinates and we have r cos theta and r sine theta and we replace the r with rho sine phi.
I just don't know why it's cosine v inside of the.
So we need one of our two variables needs to spin us around because every cross section is a circle. So if every cross section is a circle, we need one of the parameters to represent angle. So I just chose
okay.
v to represent angle.
Gotcha.
And then u is measuring how far we are from the yz plane. So u is measuring how far we come this way, and then how far we come that way, and the radius of the corresponding disk are related by that formula right there. So this will be a better way to parameterize it because then we can say u comes from 0 to 9, and v comes from 0 to 2 pi. So we have constant limits then, so that in our UV plane we just have a rectangle.
Oh, that's nice.
So now the way that you suggested will work. There's another way to do it, and we're going to look at another one in a few minutes that we do explore the other way to look at it, but it's much more complicated because the limits aren't as simple.
Because it's kind of like where when we had problems where at the top it was like z had a constant interval, we chose that to be.
So if we
something
have
that was similar.
constant limits on one side but then variable, like if we think about a circle, then if we don't use polar, didn't we have to go from minus square root of stuff to positive square root of stuff? So that's the difference.
I have a quick question.
Yeah, go for it.
And then, so then on that one, like if it was the ellipsoid instead is where the coefficients would have changed, it wouldn't have been the square root of 9 minus u would have been a and it would have been b.
Exactly. That's where we would adjust this radius.
Okay.
Because here it's the same in the y direction and the z direction
It's a
because
circle.
it's a circle.
Okay.
But you could adjust it based on that.
Okay.
All right, let's take a look at one of these spherical cap problems. There's a few of them in the homework. So S is the cap of a sphere excluding the base. We're in 14.7, so we're just thinking of it as a surface, not a solid object. And X is going to go from 3 to 5. All right. So X equals 5 is going to be the tip of the sphere, right? That's all the way out at the front end when X is equal to 5. When X is equal to 3, let's plug the 3 in right there. So let's take that 3 and plug it in. That gives us this equation. So this is going to be the projection into the YZ plane of the base of the cap. So we've got our full sphere, and we're looking at the front cap, and we're chopping it off at x equals 3. So we're going to have a little circle right here where x is 3. We eliminated the x, so that projects it into the yz plane. Okay, so another way to think of it is that you could think of this as a cylinder. There's no x in this, so it's like it's a cylinder pulling out in the x direction, and then it will intersect the sphere, and we're going to create that spherical cap. Okay, so y squared plus z squared is the boundary curve C projected into the yz plane. So let's parameterize the C, the cap. Now I'm going to just draw it this way, even though it's not this direction, but this is the idea, right? Where this plane is x equals 3, that base. Right? So we're dealing with that little cap, and that plane that forms the base is x equals 3. So x equals 3 is that right there. Okay, so to parameterize it, pretty simple. We have a circle of radius 4 centered at the origin in the yz plane. That's 4 cosine, 4 sine. Right, that gets us a circle. But then we're in the x equals 3 plane. So the x component is going to always be 3. So that will get us our parameterization. Take the derivative of the parameterization, and we have that. So now with Stokes' theorem, we're going to evaluate the field with our parameterized curve. So f of our parameterized curve. So we are going to do FDR over the curve is going to be the integral of the vector field with the parameterization plugged in. 2y, so that's 8 cosine of theta, or t, 8 cosine t, minus z, so that's minus 4 times sine of t. This is a vector field. And then the z component, x minus y minus z. So x minus y minus z. This gets dotted with r prime. 0, negative 4 sine, and positive 4 cosine t dt. All right.
T from 0 to 2 pi?
And 0 to 2 pi, because we're going around a circle. Thank you. So when we dot this stuff together, when we dot this, get back over there. All right. So when we dot that all together, we end up with hopefully something simplified. Certainly 0. So then we have positive 16 sine squared. And then for the last component, it looks like we have 12 cosine t, and then minus 16 cosine squared of t. I'll write it this way. Get that?
You got one more, right?
Yeah.
Yeah, you missed this.
Is there one more?
The,
Oh, the very,
yeah.
yeah, the last one. Thank you. So then minus 16 minus 16 sine t cosine t. Okay, then we're going to integrate all that. Now, if we're clever, we can sort of think about this piece right here. Isn't that really just a cosine of 2t?
Times
Negative?
16.
Yeah, a modified cosine of 2t. It doesn't matter if it's positive or negative. When you integrate it, you get sine.
So it doesn't matter.
And sine evaluated at those two endpoints is going to be 0.
The other two are going
So
to
you
be 0.
what's that?
Yep, I mean, that middle one's going to be 0.
And then they're both going to have a sign. And
This one's all
So,
0.
so is everybody okay with that idea that this stuff is going to integrate to 0? If it's not 100% clear, use the power reduction identity. Rewrite this as 1/2 minus 1/2 cosine 2t. Rewrite this as 1/2 plus 1/2 cosine 2t. You're going to get a bunch of cancellation.
is that okay on the test?
Yeah,
Like,
that's okay on the test.
everything has a sign.
Yeah, that integrates to sine, so on an interval 0 to 2 pi, yeah, that's totally fine. All right, so let's integrate just the other pieces of it then, since we already did one of these cosine of 2t things a minute ago, or sine of 2t things. Or cosine that integrates the sine, whichever. Okay, so when you integrate cosine, you get sine. So that one's going to go away too on this interval. And how about when you integrate this? If you wanted to, you could convert it to sine of 2t. But isn't this just direct u substitution?
With u as sine.
With u as sine. So if this is u, then this is du. So it's really sine squared over 2. So we're going to get sine squared over 2. So we get minus 16 sine squared divided by 2. And that's 0 to 2 pi. That's all going to be 0. So another one. Another one. Another. Oh.
Question.
Yeah, sure.
Couldn't you also, because since there's a negative in front, couldn't you also do u sub the other way?
Yep, you
That would
could.
be
Definitely.
Cosine.
Cosine squared over 2. Yep. That would also
But then it
work.
wouldn't be 0.
So, yeah, so if you let this be
Or would it
u,
be 1
then
minus
du, it'll still be 0.
Yeah.
Yep.
Can you just scroll up for a second?
Sure.
Better still be 0.
Yeah, it better still be 0, right? All right, let's take a break there, and then we'll start the last section. 14.8.
Can't help but feel like a lot of the problems that we're practicing are all going to come to 0, but I don't think it's going to be that way in the exam.
Unpause.
So I just figured out that
Depends on your definition already.
this was all
Ready means
like
You
you're
don't have
awake.
a choice, do it.
Oh,
Notes
oh.
on
what we just
by the
did.
way.
I know, I was
Right.
noticing that. I
Which,
don't know how
when
they got all
did you
tangled
do
up.
that?
So,
Because
So
that's
I
weird, because I
printed
printed
double
this
notes.
out like
A
a month ago.
Yeah.
It was a long time ago.
Yeah, they got messed up on this last section.
And this is
There was a
all-
little divergence. Oh, look! The divergence theorem. 14.8.
Oh, look!
The culmination.
This is it.
Oh,
my
for this.
Made it through the book.
All for this. This is what you've been waiting. 1,000 with some squash bean. That thing. Like, it's all about that.
The culmination of human knowledge.
Culmination of human knowledge.
All of the basic human
This
knowledge.
entire book. This book right
Right up to that. I feel disappointed.
there. That's really what it's all about?
Almost made a
It's
rookie
like doing
mistake.
a problem
Yeah,
super long and then you
Yeah,
that's it, I'm back.
It's all boiled down to
you
that
walk
bean
in here.
looking thing.
What do you want?
This.
Never found it again.
All right. So the divergence theorem is just the flux form of Green's theorem in 3 dimensions. So Stokes' theorem is the circulation form of Green's theorem in 3 dimensions, Stokes' theorem, and then the divergence theorem is just the flux version. So let's take a look at it. So in 2 dimensions, we have a region with a boundary, and the single line integral on the left here represents integrating or adding up the normal pieces of the vector field. So this says add up all the normal pieces of the vector field, and that's equal to the divergence happening on the inside. So on the outside, you're adding up the normal components of the field. On the inside, you're accumulating all the divergence. And those are equal. So conceptually, we say that the divergence is the volume per unit of time leaving the inside. And the line integral side is the volume of unit per unit of time passing through the boundary. And of course, those have to be equal. Right? The net leaving the inside has to match the net that passes through the boundary. So the normal component is measuring the stuff perpendicular, the field components perpendicular to that boundary curve. Now, up the ante to 3-dimensional space, and we have a solid object. Same thing is true. The divergence from the inside of the solid has to match what's passing through the surface. So that's what this says. So now the double integral is a surface integral because all these vectors that are pointing off of our solid object there's a normal component to them, but we're integrating across a surface. And then the inside is a solid, so we're integrating throughout a solid object, so we have a triple integral on the right. So the divergence of the field throughout that whole triple integral gets you a net volume per unit of time leaving the inside. And then the surface integral gets you a net volume per unit of time passing through the surface. And those two have to be equal. So now we have a surface integral and a volume integral. Surface and volume integral.
It's D. Is it just divergence?
D is solid object.
D is a solid object.
That thing right there is a solid object.
What's a chicken
Okay,
nugget?
they couldn't. Okay,
They couldn't what?
they couldn't use. I don't know what letter they would use. That would be better.
Because they
actually,
can't use
but-
surface.
Yeah.
Okay, we're
Some books use a G.
okay.
I'm not sure why they would use a G either. Yeah.
It's a chicken nugget.
I'm gonna use this.
They should
It's a
use-
chicken
They should
nugget.
use it.
Yeah, it
It's a
looks
nugget.
yeah, that has the same. Yeah, looks about the same.
And for nugget.
They could have done anything cooler. They could have made it look like a space nebula or whatever.
know.
But they had to make it.
You make it look like a
brown.
chicken nugget. Yes.
The color of a hero.
That's the advantage of these black and white ones. It leaves a little more to the imagination.
You can create your own
It
image.
can be
Okay, so here's the divergence theorem. And there's all these things, again, we really don't have to pay attention to all those conditions. The surface is a nice surface, the partial derivatives exist, it's a simply connect, all that stuff, we just ignore that.
Until you ask us it on the test.
You will not be asked that on the test. You will not be asked that on the test. So we're much more focused on how the math unfolds between the surface integral and the volume integral.
Wait, they equal each other?
Yeah, so this symbol right here, we're finally to the point where that symbol,
Does not.
we
mean
can say
equal.
that it means equal. It means equal.
Yay!
Finally.
Wait, I thought the only way to go from a triple integral to a double integral is the triple integral is of 0 or like 1, and the double integral
This is
of a
totally
function.
different.
Completely different.
Completely different. This triple integral and this surface integral
We get a note.
are related in a much different way than what you were just talking about. Yeah. So when we were dealing with regular Cartesian coordinates, what you said is right.
And this is like abstract.
Yeah. So now it's different. So now, so back then, a double integral of a surface would equal the triple integral of one
The volume.
volume.
And that is why we get a note card.
That's why you get a note card for the final.
Will we get a note card for final?
Yeah, dude.
Yeah. In exchange, you have to look at what the contract says.
The what now?
Can't put like
Which contract?
I'm okay with
So
that.
you have to give me a epsilon of your soul.
And our first word
List all
child.
those epsilons and create a chicken nugget. Okay.
Should have known this was your lord.
So let's take a look at both sides of hopefully the accumulation of your epsilon soul pieces have more nutritional value than a chicken nugget.
Doubtful.
There's no way.
There's no way. Okay, so everybody follow how we find the divergence of our vector field. So divergence, we go in order, partial with respect to x, and then y, and then z. So
That's
in
very
order.
nice.
So not like that flux where we did g sub x minus f sub y.
Or the curl where you had to do like the big old
Or the curl where you have to do the big old determinant thing.
thingy-mabob.
So we love divergence. It's easy, fast and easy.
Love.
Partial with respect to x, y, z. And you add them together. It's not a vector, it's just a function.
So that would be 2 plus 2 plus 2 or 6?
Those are all different letters though, so we can't combine them.
Well, we will for the normal, don't we? We just pull it out, and just have an n, and n equals 2, 2, 2.
Okay,
I
so
think
going
we're very
on.
confused.
Moving on, these are not like terms, so we can't combine them. The triple integral side of the divergence theorem is going to be this. So then we have to do a dx, a dy, and a dz. And it doesn't matter the order here because we're dealing with a rectangular solid. So x is going to go from -1 to 1, y is going to go to -2 to 2, and z is going to go -3 to 3.
How do you know that? Sorry.
So this says that x is between -1 and 1, between -2 and 2, -3 and 3.
Absolute value.
Oh.
Absolute value.
I see, I see, I see.
All right, so that is the triple integral side. That tends to be the easier side if your divergence is a simpler function. So there is x, y's, and z's, so we can't just collapse anything, unfortunately. But this integrates pretty easily. Integrate with respect to x, we're going to get x squared plus 2xy plus 2xz from -1 to 1. let's evaluate that. And that evaluation, let's see. Do you agree that the x squared
All
part?
this is going to work out right.
That's going to go to 0, correct?
Yes.
0. Plug it in 1, subtract off what you get when you plug in -1, so that part goes to
Isn't
0.
it all going to
I
cancel
think you
out?
should all of it cancel.
I don't think so.
I think so.
Two
Oh, wait, no,
y
I don't
minus-
think
I
so
don't
either.
think so. So we get 2y plus 2z minus
Because you're subtracting a negative.
what happens when we plug in the minus, so then it's
Yeah.
going to be plus 2y plus 2z. It's only the one with the square that's going to vanish.
Yeah.
We certainly have like terms though. And when we integrate now with respect to y, we have 4y, so we're going to get 2y squared. So I'm combining those two, and then let's combine those two. 4z integrated with respect to y, so we get 4yz. And here the y squareds will go away.
I'm seeing a pattern.
We're seeing a pattern. Seeing a pattern. That's gone. So then we're going to end up with the integral from -3 to 3 of what?
16.
16z.
Hey, I think
So we have
it's
8
gonna cancel.
plus 8. And then we get 8z squared. Now we get 0. 8z squared.
Took a
And we go
while.
3 to 3. There's our 0.
See, this is one where we couldn't just get to 0 in the first step.
There's our 0. But so let's think about that. So the divergence was not 0. So what this tells us then is that there's just as much of this fluid, if we think about a fluid mechanics problem, entering this solid as there is leaving. Okay, so it's not that the divergence is 0, it's that there's as much coming in as going out. So if the divergence is 0, that just means none is leaving the inside, so you'd have a triple integral that's also equal to 0. This says there's just as much coming in as going out.
Wait, so the divergence that we originally started with is just how much is going out, and then we calculate the total in and out? with
Yes,
the- okay.
then we calculate the net.
Okay.
So that divergence up here is telling us, that's the divergence, and then when we do the integration, that gives us the net.
Okay.
The net that's leaving, the amount leaving combined with the amount coming in.
And then this is the flux, like, right?
Yep, this is flux.
Okay.
This is flux, right. So we could put this out in front. We could put one of those fancy flux symbols out in front. You know, one of those.
symbols.
The little capital phi. That's capital
One of those
phi.
TIE fighter,
Sideways TIE fighter.
one of those things. One of those Star Wars things.
Yeah, I think it's a TIE fighter.
Is it a TIE fighter?
Sideways, but yes.
But that's capital
Yeah,
phi.
well,
Capital
right?
Phi.
Nothing going sideways.
Cap phi.
There's no up or down in space.
No, exactly.
Yeah, which Star Trek doesn't seem to understand.
Right.
How do they not understand it?
Because the Enterprise is always like,
works like a naval battle in Star Trek.
Haley,
Oh, it's leaving me. No.
is it gone?
No. Wait. Oh, so divergence, what Andrew said, so the two-dimensional divergence, he said that that's just what's going out, or if it's negative, what's coming in, and this is the net.
Yes. So at every single point on the inside, you have a value for divergence. You have it's either coming or going, and then the integral sums all those up.
But the
So it-
divergence in 2D is not that. It's
Same
not-
thing,
it's
same
not
thing.
net. Is it net?
Yes.
But it's just two-dimensional.
The integral is net.
Okay.
So the integral adds up all of the little ins and outs to give you a cumulative flow,
Okay.
whether you have a source or a sink or neither.
So they're both net. once
Yes,
you
they're
integrate.
both net. The integral is always adding up all of the individual little pieces. So if you imagine divergence at every little piece defined as leaving or coming or going,
Okay.
that integral adds all those up and gives you a net flow out, in, or balance.
Okay.
Yep. Okay, so that's the triple integral. So now we're going to do the surface integral. So to do any surface integral, we have to parameterize the surface. Oh my gosh, this looks horrible. So we have a rectangular box.
Oh, no.
So what would we have to do?
Do every single one.
We would have to do all 6 faces, the surface integral for all 6 faces. So let's do 2 faces.
Nah.
We'll do 2 of the faces, and then you can extrapolate from those 2.
Could we do 3 and then just do the other half because they
We-
should be the same?
We could do that.
Like, is that a viable option? Like, could you do 3 and then double?
Well, it all depends on the function. It all depends on the value of the field on each of those surface faces.
Okay.
So let's see if we see a pattern. Maybe the 2 x faces will add to 0, the 2 y's will add to 0, and the 2 z's will add to 0. So let's first parameterize our surfaces. So surface 1, we had, let's go with x's first. So surface 1 is the surface x equals -1. Okay, now we have a solid object, and the normal has to be the outward normal so that everything's lined up. Flux positive means something's leaving the inside, so we want outward normal. What is the outward normal for x equals -1?
1, 0, 0.
Outward normal, what did you say?
1, 0, 0.
So if we think about x equals -1 is here and x equals 1 is here, the outward normal has to be pointing backwards.
So -1, 0.
-1, 0, 0. So it's pointing backwards. So its normal is going to be -1, 0, 0. So the 2 possible normals for x equals -1 is to point forward, which would be 1, 0, 0, or to point back, which would be -1, 0, 0. And since this is the back face of our rectangular block, we want it to be -1, 0, 0.
Is that capital N or is that a not capital N technically?
In this case, you could also call it a capital N just because it is a unit normal.
Okay.
But in the way they've drawn the theorem, it's just that N
Okay.
that shows up.
So this one can be 1,
So
0,
lowercase
0.
n generally means it's been normalized.
Yeah.
So one of the things that we need to add to our like math toolbox is a coin with big N and little n on each side, and you just flip the coin. And
Yeah. Yeah, it's very funny that because I feel like it adds confusion when in the theorem they mean it to be a unit normal, and right all along we've used capital T and capital N as unit. When we were doing acceleration, that was a unit. So I don't know why they did that. All right, so let's. I don't know why I'm writing so much down. We'll write down these first 4. Ooh. So y equals -2, that's on the left. So the outward normal is going to be 0, -1.
what? I didn't say that.
Can it be 0, -1?
what a
Because
figure
if you
of
just divide
imagination.
everything by 2, then you get the
Well,
same
so
thing.
if you think about this as a surface, it's 0x plus 0x plus 1y plus 0z equals 0. So the normal is either 0, 1, 0, or if you multiplied it by -1, 0, -1, 0, and then you have to just pick the one that's outward. So for this surface, we're picking the one to the left. Y equals -2 is this plane, y equals +2 is this one. So the outward normal over here, y has to be -1. The outward normal over here, y has to be +1. So it points to the right. So now let's look at our field. So our vector field, x squared, y squared, z squared. All right, so surface integral. So we're doing double integral, let's see, over S1. And let me just take you back up to the top for a second. So, or I guess it's on the previous slide. So the surface integral side, we are going to dot the field
R perp.
with, not R.
R prime perp.
No.
Why are you panicking?
I'm panicking because you both are talking about curves and not surfaces,
Oh, okay.
right? R prime perp is for flux when we're dealing with a curve. We would turn the dr into dr perp, and so we don't multiply by r prime, we multiply by r prime perp. This is a little different. This is a surface integral. So just think what we just did with curl, right? Didn't we just dot curl with n? So that's what we're going to do here. We do regular surface integral. We're going to dot these two together. So and here's let me write this out again because this is where the confusion is in this book. So when he writes the little n there, I would prefer that to be a capital N because the evaluation of this turns into f multiplied by a little n with a dA. this is over the surface, this is now over the region in the xy plane, if that's where our domain is. So I would rather he wrote a capital N there, because otherwise it looks like the two ends would be the same if we just write a little n like he does. It looks like they're the same ends, but they're different ends.
What a rookie mistake.
I know. I don't know why it does that. So whenever we evaluate a surface integral, we actually have to do this dot product. We calculate that dot product. So f dot n, so let's do
That's the
that.
normal vector?
That's
that
the
we
normal
just found
vector.
right there?
Mhm.
Oh,
So
that's
we
so
have
much
to
easier.
we have to take our field. Let's write our field over here. Our field was x squared, y squared,
Z squared.
z squared. So x squared, y squared, z squared. And so now we have to sub the x value. So on our plane, we know that x is equal to -1, or where we could dot it first and then evaluate with the x. Let's dot it first. So straight up dot product. This becomes -x squared, and this is now going to be a dA. So that is f dot n is right here. So let's write this as f dot n. Everyone okay with that?
Is that including the dA or just the -x squared?
Just the -x squared is the f dot n. So we dot those two guys together.
Okay.
And now, for this particular surface, S1, x is always equal to -1. So now we can replace that -1 in here, and we end up with factoring out the minus. And when we factor out that minus, we have double integral of dA over S1. So this now represents the area of the S1 face. So the area of that face.
But negative.
So we'd have to go look at the area of that face. So we have, what's the area of the face? 6. So let's come up here. So this thing here, this is a rectangular box,
3 times 1.
right?
One
The
times
y
two.
components are going, it might not be 6.
Isn't it?
It's going to be, should we try to draw it?
4 times 6 times
It's actually going to be, what's it actually going to be? 4 times 6. It's actually going to be 24.
times 2.
No, not times 2. Just the one face.
Oh, face.
The
yeah.
area of the one face. So the area of that left face, when x is -1, we have the y's going from -2 to 2, and we have the z's going from -3 to 3. So the height of the rectangular box is 6, the width is 4, so 24 is the area of that face. So if we tried to draw this box, one of the dimensions, I'm not going to try to draw it right now. Okay.
So that's
So-
-24?
So this will be -24. So that's the surface integral, so that's the volume per unit of time leaving that face. So that means it's actually going in to the solid object because it's negative. If the flux is positive, it means that it's leaving. If flux is negative, it means it's going in. So this means -24, cubic inches, whatever it is, volume per unit of time.
What happened to x squared?
We plugged in x equals -1.
Okay.
So on this face, all the x values are -1, so this can turn into a +1, well, a -1. All right, so let's do the next face. All right, next face.
24 again, I'm sorry.
Say again?
24.
So y to y is 4, because it's -2 to 2 in the y direction.
Okay.
Z is -3 to 3, so
Okay.
we have 6 high and 4y.
Okay.
So 6 times 4. Got it. So let's do surface 2. So surface 2, we have to dot f with n. So we come here, it's going to be +x squared. Okay. That x squared, now x is 1 on this face, so we get just the double integral over S2 of dA. That means the area of S2, which is the same as the area of S1. So that's going to be +24.
Wow.
So now, front to back, there's just as much coming in as leaving. So this measures how much is leaving face 2. This is how much is coming in through face 1. So let's just do one more of these with a different area, just to make sure that we're clear on how we got that area. So down here, we're going to do double integral. We dot this with the vector field, and we get y squared. Yeah, I dotted that correctly. Y equals 2, positive 1. Okay, so,
Which one are you doing?
oh yeah, I guess this is not really lined up, right? This was up there. This one, let's do this one here.
So then you get negative.
Yeah, so we're going to get negative y squared. And that's going to be s sub 3. So y on this face is always negative 2. So we're going to get 4, negative 4 outside times the area of face S3. Okay, so the face of S3. So with this face, we're dealing with the x direction and the z direction. So we're between these two y values, but the face is with respect to x and z. So we already said that z goes minus 3 to 3, so the height of that face is 6, and the width of that face is 2, from x equals negative 1 to x equals 1. So we have 6 times 2, which is 12, times negative 4, so we get negative 48. So that's how much is coming in through face 3. Now you can see the pattern. How much is going to leave through face 4?
48.
Positive 48. That's going to be 0. And then we do the same thing with the z's, and we're going to get a net total cumulative of 0. What is the area when we're going in the z direction? Then x and y form the area of those two faces, and those areas would be. So when we're looking when we're looking at these surfaces, then we're going to have 4 times 2 is 8 for the area of the faces that are horizontally oriented. All right. So we will get, etc. 0. 0. I'll have to do another one. Okay. Outward flux of this vector field on this time we just had a cube, so it'll be a little bit easier. Across the boundary of a cube. Oh, here the divergence is 0. So the last one, the divergence was not 0. Here the divergence is 0. So the triple integral side of the divergence theorem is super simple. Triple integral of 0. What do you use for a solid object? D? D. And that is 0. So that side, pretty simple. That's the perfect exam question. That will not be on the exam. Divergence is 0.
Why are we doing it?
So now let's set it up using the... So the idea, though, the point that he's trying to make here is that the triple integral is going to be simple to evaluate, but if you were to break it apart into 6 surface integrals, that's going to be a lot more complicated. That's his point.
He's proving the reason why this is actually relevant.
So that is simple. If we did it the other way, let's not go through. Let's not go through
Isn't
the
it
other
just
way.
the same exact?
Same that we just did. Same that we just did. So the big difference here is that we still have a net of 0, but for a very different reason. So this surface here, there's nothing passing through it. Right? Nothing's coming in or leaving. All right? Because the divergence is 0. So that means that this vector field inside the solid object is just circulating. There's no normal stuff. There's nothing passing through the surface. So this has a net of 0 for a different reason. There's not stuff leaving and going that is balancing out.
This one's more interesting.
This one's more interesting. The surface has a divergence of 2x. And the vector field is more curious. Okay, so let's go ahead and do the triple integral side of the divergence theorem. So triple integral dx, dy, dz. And we know that we can just do dx, dy, dz in any order because, again, we're dealing with constant limits of integration.
0 to 1 for all.
So we're going to go 0 to 1 across the board. and integrate with respect to x. And we get x squared, 0 to 1. So what do we end up with total? 1.
Nice.
Not 0!
That's the first problem we've done today that didn't equal 0.
Didn't have a 0 in it?
We're checking off the binary list.
I don't know why.
Yeah.
Okay. All right, so now let's do.
Right.
I forget how many slides we have today.
Just one more after this, I think.
Okay, oh, we have the cone one. Okay. So
Yeah, right.
let's set up some of these faces. Let's just do a couple of faces. This one's going to be a little bit different. So, is it clear how to find the normal vectors for each of these faces?
It's planes, right?
Yeah.
So those are all planes, so they're either going to be, there's going to be a 1 or a -1 in whatever position it needs to be in. Yeah,
Normal is going in or going out?
out.
Out, okay.
So divergence, we're going to have positive flux if there's stuff leaving the inside.
But the normal we want is like out from the box, not going into the
Right,
box.
it's going out because that's going to give us a positive number then if there's movement in the direction of that normal.
Okay.
That's going to give us positive flux. Right, exactly. So let's do the bottom and the top surfaces. So let's call this S2 up here and S1 down here. Let's do those two. So S1, the equation for S1 is Z equals 0. The equation for S2 is Z equals 1.
Is S1, sorry, is S1 the bottom one?
Yes.
Okay.
Yeah, S1 is the bottom, S2 is the top. And for this surface right here, what is going to be the normal that points out? 0, 0, -1. And the normal for this one that points out? 0, 0, 1. And our vector field, let's leave that. So we're doing a surface integral. So surface integral means that we have to take f dot n. So we're going to take f, dot it with n. F dot n, and this is over S1. That's going to be a ds. Okay, so this is going to be the double integral over S1. F dot n looks like minus y squared. And I can change that S1. Let's go into what the differential should be. So this is going to be over R, and this is going to be a dy dx, or we can just call it a dA for the time being. Okay, so this surface, z equals 0, the dA definitely is dx's and dy's. So how about that function? Is there any simplification that we could do like we did on the last one? We can't, right? The surface is z equals 0. So there's no z in there, so there's no way to take that and reduce it like we did above. So that is just our function. We integrate it. And we are going to integrate with respect to, let's go with respect to y first and then x. Now dy dx, because we have a square, these are easy enough. We just go 0 to 1 for both of those. That one over here.
And again, we just equal 1.
So this is going to be, let's see, there's no x's nor will there be any x's, so we can multiply by 1. We're going to get minus y cubed over 3. 0 to 1. So we end up with minus 1/3. So that means that through the bottom of this cube, stuff is going in. So there's volume entering the solid from below. Now let's try this face, the opposite face, and see if we get cancellation or if we get a little accumulation. So here we're going to have double integral over S2 of f dot n ds. That's going to end up giving us, so 0, 0, 1. So we get positive y squared. We can go dy dx. Again, it's going to be 0 to 1, 0 to 1. what does that end up being?
1/3.
1/3. So,
Same pattern.
but we know that we're not going to get 0 in the end. So this says there's 0 net between top and bottom. There's got to be some accumulation between the other two faces. Which face?
To get 1.
To get 1. So
I
we
don't
don't
know
know.
which
I think it's
Yeah.
the middle.
Yeah, so probably because there's a y in there,
It's probably the
it's
middle.
probably in the y direction. So let's check one of the y faces. So let's say S3, let's let that be y equals 0, and let's let S4 be y equals 1. Let's just check these two. So the normal vector for this one, y equals 0, is going to be 0, -1, 0. And the normal vector for this one is going to be 0, 1, 0. And then we go to our field. We have to dot. So we're going to have double integral of f dot n ds over S3. Okay, -1 dotted with our field is going to give 2xz. Once again, our domain is a rectangle, so we can just put constant limits here, 0, 1, 0, 1.
Is it negative?
It should be negative, thank you. And then we integrate with respect to x, and we get negative x squared over 2, negative
My negative x squared.
squared over 2z, 0 to 1 dz. Do you agree with that?
It's times
No.
This
2.
one.
2, there should be not.
There's
should
no-
not
Oh, the 2 cancels, thank you. So we get that. Plug it in the 1. Looks like we're going to end up with negative z. So we get negative z squared over 2. So we're going to get negative 1/2 total. Negative 1/2 total. Negative 1 over 2. All right, there's some accumulation, except in the wrong direction.
Why do you say there has to be some imbalance somewhere? There has to be some accumulation.
Because didn't we get a 1 up there?
Yeah.
Right, so we have to end up with a 1 total when we add up everything going through all 6 faces. This is not helping though, that's taking
Oh,
away.
it's because the triple gave us everything.
Yeah, triple gave us everything all at once.
Okay.
That's why that one's usually easier. Okay, so then let's check this face and see which direction our accumulation is going. The faces are all 0 to 1, so that's pretty easy. Now we get a positive 2xz. So this looks identical to that one, so this one's going to have to be a positive half.
It is.
So it's got to be the other two. We're too curious not to at least do one of them, right?
Nope.
We have to do one of them.
Not
Okay.
Sorry.
Not curious. Yeah, not curious.
Curiosity killed the cat.
Curiosity is dangerous.
I'm curious.
Okay, so what's the last one? We didn't do the x's. So x equals 0, x equals 1. God, forget that. So n when x is 0 is going to be negative 1, 0, 0. So it looks like that vector field is positioned in a way that is more important to us than actually more than what we realize, I guess. Okay, so dot negative 1, 0, 0, and we get so negative x squared. So this would be a dy dz.
Oh, this is what's different.
All right. So what does this one give us? So there is no something fishy though. Did I do that? Do I have the right differentials there? So x equals 0 is here, so it should be in the yz plane. That x is not cool though. We've got to turn it into y's and z's. So let's go up here. How do we turn that into y's and z's? Let's see. On our surface, oh, x is 0, right?
So it's just 0.
So this one is 0.
This is it.
So it's
This
all
is
the way down to 90
degrees.
degrees. How did we pick this one as our very last one? How did we do it?
Conspiracy.
1! Oh, we found it. Lo and behold. 1.
Wow.
Because x is equal to 1, so 1 squared is 1, so then we get 1 times 1, which is 1.
Wow.
That's the face we've been looking
Wow.
for. The last face.
We should have started with our x's. Always
Just
start with
x's.
We learned now. We've learned.
All right, well, that's funny. All right, we ready for a cone?
Yeah.
No.
I'm ready for
It's our last problem, guys.
Is it an ice
It's
cream?
our last problem.
Now this last problem's long.
Okay.
Let's put on our seatbelts.
Okay.
We're gonna do this one in a few ways.
That's all right.
Just
Take
to
it again.
keep Jalen engaged.
No thanks.
She's
I'm
so
good,
curious.
Actually, never mind. Not sad.
She's so curious.
I'm gonna miss it.
All right, everybody agree the divergence is 3? Oh, we didn't do either of these two yet.
It does say
Oh, we did.
that divergence is 3.
Yeah, I wrote that.
Agree with that.
But do you agree that it's 3?
Yes.
Yes.
Not because of
One
that,
plus
but do you
one
agree
plus
that it's
one.
that it's 1 plus 1 plus 1?
Yeah.
Do you agree
Okay.
that 1 plus 1 plus 1 equals 3?
I do.
Awesome.
I do. I'm with you.
Prove it.
I'm with you, Grasshopper.
That is geometry.
Okay.
1 plus 1 plus 1 equals 3.
All right, so this cone is what I was thinking about earlier, where it's a solid object, so if we do the surface integral, we have to do the cone plus the disk, because it's a solid object, not just the boundary, like we did in 14.7. Okay, so surface of this cone, z is going 0 to 4, plus its top, in the plane z equals 4.
Because it's a solid object.
Solid object. It's got to have, you know,
Close.
it's got to be closed. Okay, so let's go ahead and let's do the triple integral piece first. So the triple integral side of the divergence theorem, we integrate the divergence over the solid object. All right, so we have a pretty simple way to do this. This is going to be 3 times the volume of the cone. So volume of a cone is 1/3 pi times the radius squared times the height. The height of the cone is definitely 4. How about the radius of the cone? So if we're going 0 to 4, when z is 0, we're down here, and by radius we mean the radius of the base. Isn't that also 4? Everybody agree? So it's going to be 4 squared. So those cancel, 16 times 4, so we get 64 pi. So this is using the triple integral.
Is it 2 for radius?
Yeah, how did you get 4 for radius?
I don't know.
Solid.
When I plug in a 4 there, I get x squared plus y squared equals 16. Square root of 16 is 4.
Okay.
Alrighty then.
Good job.
I'll take it.
Pressure. 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 Just seemed right. Just felt right. Felt like it had to be a 4. Okay. So, there we have it. Now, if you didn't remember the volume of a cone, you could convert this to cylindrical coordinates and find the volume of a cone. Let's do that because one of the topics on the final exam does have to do with cylindrical coordinates. So what if you needed to calculate volume of cone? So if you didn't remember, or if you weren't told, or if it was an object that you didn't know the volume of, how would we find the volume of this cone using cylindrical coordinates?
Use a triple.
Yes.
Of 1.
Yes.
Go dz.
Triple
R,
integral of 1.
dz r.
So
Jacobian.
now when we're dealing, no Jacobians. When we're dealing with volumes, we have to think about we have to decide, should we talk about the volume between these two surfaces, or these two surfaces, or these two surfaces? So vertical surfaces, regular surfaces, this way. So then we could do a triple, or we could do a double of upper minus lower. So a double of upper minus, or a triple. Let's set it up as a triple first. So triple, I'm going to factor the 3 out to the front. So cylindrical coordinates, we're going to have a dz, dr, d theta, but then there's also going to be an r in there. So r dz, dr, d theta.
You
Cylindrical
lied.
coordinates.
I like to do DC.
You
Why?
said there's no Jacobian. There's obviously a Jacobian.
Not a Jacobian that we have to calculate, though. We're not going over and doing some determinant. We know that in cylindrical we have RD, RD theta.
RDZ, RDZ,
RDZ, RD theta.
RD theta.
RD, yes. RD, yes. Yes! All right, so what's the lower surface? What's the lower surface?
0.
No.
Oh, the cone.
The cone! The cone. So we're imagining a vertical element that's touching these two surfaces. So one of the surfaces is the cone, and the other surface is that disk up top.
Which is equals.
Right. So this is the lower surface. The cap is the upper surface. What is the lower surface in cylindrical coordinates?
R.
R. R squared?
No.
Just R.
Just R.
Just R.
Why is it just R?
Right? If x squared plus y squared is r squared.
Yeah, and then-
Take the square root of both sides. We're dealing with positive z values. So z is equal to r.
R to 4 then?
Now what is the top surface?
4. Z equals 4.
Z equals 4. Very anticlimactic. Okay. And then r goes from
0 to 4.
0 to 4.
0 to 4. And theta is
0 to
2
2 pi.
Yeah. So there's it. That's it. Yeah.
And that should be 64 pi.
It should be,
Correct.
it better be 64 pi. Should we check? So we have
Yes.
3. There's no thetas coming, so multiply by 2 pi. We definitely have some r's, so we'll leave this integral 0 to 4. This gets integrated with respect to z. There is no z, so we multiply by the length of the interval. So it's r times 4 minus r, which is 4r minus r squared dr. And hoping for the best, we integrate with respect to r. Evaluate 0 to 4. And we get 32 minus 64 thirds. Yeah.
Which is 64 pi.
Did it work? All right, so we have 6 pi times 32, and if we change 32 to thirds, that's going to be 96 thirds. 96 thirds minus 64 thirds. That's going to be 32 thirds, which is 64 pi. And we multiply by 6. 64 pi. All right, so that worked. That's a 64 pi.
Is this the long? Wait, wasn't this long?
Not yet.
Okay.
When we do the surface integral pieces, that's going to be the longer part. So this was just the triple integral side. The triple integral side of the divergence theorem is often easier.
Then why do we use the other one at all?
To verify that they are equal. To practice our surface integration.
Because math hates you.
I'm going with that. Okay. So now, this is the volume side, the triple integral side. Now let's do the surface integral side. So we have to parameterize our cone, we have to parameterize our disk. And
So do you have like a C1 going up the one side of the triangle?
S1 and S2.
S1 and S2. So one is going up the side of the cone and one's the top of the cone?
So the parameterization of the cone. So R of U comma V equal. Have faith. You can do it. Cone.
U, comma, V.
No.
Squared equals.
Wrong.
Shut down.
So the suggestion to let X be U and R be V or Y be V, that is a method of parameterizing it, and then you would let Z equal the square root of U squared plus V squared. But the problem is the limits again. The
Yeah.
problem is that we didn't take into consideration the roundness. And so then our limits are going to be just like this kind of thing, where we have to go from negative square root to square root, and it's going to be quite complicated. So it's better if we can build the roundness into our parameterization.
Could we potentially use parametric coordinates like r squared equals z squared, so we do u squared equals v squared possibly?
Bingo. So we have z squared equals r squared, so r is going to equal z. We're dealing with positive numbers, so that's fine. So the circular part tells us when we do the r cosine theta and the r sine theta, then instead of r, we're going to put a z in there. Right? So whatever we let be z. So in other words, z is the free variable. Right? Z is going from 0 to 4, and then we're going to try to build our disks where z is the coefficient. So z is going to go 0 to 4, so let's do this. Let's start with z, and we'll let z be v. Sure. So if that's v, then over here we have an r cosine of something and an r sine of something, but isn't it true that r and
It's just v.
so yeah, so it's going to be v cosine of u, v sine of u. That'll do it.
So then v is going 0 to 4. And
Then
u
v is going 0 to 4,
5.
and exactly. So v is going to go.
No.
Bless you.
Thank you.
Right. So those are our limits. So now we have nice limits, square limit, rectangular domain. Okay. So now we need a normal to this cone. Right. To do a surface integral with flux, we have to take f and dot it with n. So
Can
we
we
need
do
to find.
0, 0, 4?
Say again.
Can we do 0, 0, 4?
When we're dealing with the disk, we can do something like that.
We're doing
Yeah.
the
But we're
cone.
doing the cone right now. So normal to the cone, we're going to do r sub u and r sub v, and then cross them. So r sub u is going to be minus v sine of u, v cosine of u, 0. And then r sub v is going to be cosine u, sine u, 1. So those are the two partials based on our parametrization. Cross them, that'll give us a normal. Crisscross. So we're going to get v cos u. And then the middle component is going to be 0, so v sine u. And the other component is going to be,
V cosine 2. V cosine
so just
2.
minus v.
Y minus.
Because it's so the last component we do this direction, minus v sine squared, minus v cosine squared, sine squared plus cosine squared, where I get minus v. So that's our normal vector. So now we're going to take our field and dot it with our normal vector. So the surface integral is double integral of f dot n ds over this cone. So now we're going to have double integral of f. And we have to go up to f, and we have to put the parametrization in for this surface. So it's going to be messy. So let's get up there. Where is f? Way up there.
X, Y, Z.
Oh, that's an easy one. X, Y, Z. Okay, so we have X, Y, Z. So it's going to be v cos u, comma v sine u, comma v. So this is f evaluated at our parametrization. So we took our parametrization. There's x for our parametrization. There's y. There's z. And we plugged them into the x, y, and z. Now we have to dot that with the normal vector. V cos u, v sine u, minus v, and this is du dv, or dv du, doesn't matter. We have a nice parametrization where we have limits that are constants. So get that.
We should have big time cancellation.
Let's hope.
All cancel.
Let's
I think
hope.
it's 0.
Cancellations.
Does it all cancel 0?
It shouldn't be because we've got 64.
But we still have the
have another
disk.
one
We
to
still have the
check.
disk to do though, so this could all cancel. So we have v squared cos squared plus v squared sine squared. That's v squared
Minus v squared.
minus v squared. All right. All right. That's,
So we
that's
better just
0.
hope the other one goes to 64 pi.
So we better get 64 pi on the other one. So now we have to parameterize that one. So again, this is a little fishy. So we want to parameterize that. That is circular though. So if we tried to parameterize it like we would a regular plane where we do something like u comma v comma 4, then the limits are weird and difficult. So what we would like to do is parameterize it taking the shape into account and creating a circular, taking the circular piece into account. So when we look at that disk, the z values are all 4, right? But it's a disk, it's x squared plus y squared equals 16. So let's see if we can parameterize it using that idea. So let's do the disk. So r of u comma v. So the z component is going to be 4 for every point on the disk. And we just want to do, did we use v as, we used u as the angle up here, so doesn't this do it if we just do this? V sine of u. And u is going to go 0 to 2 pi. And v goes from 0 to 4. Everyone agree that that will give us the entire disk, not just the boundary of it, but the whole disk. So as v changes, so sine of u and cosine u take you around in a circle of radius v. And so so we're sort of imagining a bunch of concentric circles to build that whole disk. When v is 0, we get the point in the center. When v is 1/8, we get the circle of radius 1/8. And then we keep going until we get to v equals 4, and that's the boundary of the disk. So that's the whole disk. Now, we parameterize this. We didn't use a regular Cartesian parameterization. The normal vector is not going to be 0, 0, 1. If we parameterized it u comma v comma 4, and we did ru, rv cross them, we would get 0, 0, 1. We will not get that here because we have this circular stuff going on in the parameterization. So let's not just jump to conclusions that we're going to get 0, 0, 1. We do r sub u. We do r sub v. Excuse me, I'm not done with r sub u. R sub u. We do r sub v. So the parameterization is that's what leads you to the normal vector that you're going to choose. And we've seen with planes that you can do the xyz thing with the coefficients, but that's only if you're dealing with Cartesian. So now we cross to get our normal. We're going to get 0, 0.
V?
I think minus v.
Yes.
0, 0 minus v. Whoops.
Negative v. And then
0, 0
minus
minus v. Get that. So now we need to choose for this surface the normal vector that's oriented properly. So the way that we have our solid object, we're looking for outward flux. So the normal that we choose better be pointing up out of the surface and not in. So we always have to ask ourselves when we find our normal through the mechanics of the math, we have to ask, is it the right direction? Or do we have to multiply by -1? So we come down here. This normal is pointing inward, right? Because v is positive between 0 and 4, so that's pointing in, 0, 0, negative number. So this is the inward normal, which implies 0, 0, v would be the outward normal. So that's the one we want, outward normal. Now we're almost there. So we take our parameterization, we put it into the field, And this field was just that radial field XYZ, so that's pretty simple. So we just plug we're going to have V cosine U.
So yeah, how can we justify just switching the normal around?
So with all these theorems, like with the divergence theorem, it says we're measuring outward flux. So that means that any surface that's part of the boundary, the normal that we choose has to be pointing outward.
And this is not pointing outward, so.
Yeah. So we multiply by -1, and it's going to switch it from inward to outward.
Okay, so sometimes we need to switch it.
Yep.
Okay.
So if you, like the last cube thing we were dealing with, the couple problems ago, if you were to find the normal by doing the XYZ coefficients, we had a couple of them that you had to switch because it was pointing in instead of out of the cube. So you always have to check that the normal that you get mathematically is pointing in the direction that orients the surface properly. Okay, so then this is the field evaluated at our parametrization, and then we have to dot it with the normal. So 0, 0, V, and that's going to be du dv, and our u's were 0 to 2 pi, and our v's were 0 to 4. So this one we're hoping is going to give us everything. Dot this together, and what do we get? 4v. So we get 0 to 4, 0 to 2 pi, 4v du dv. No v in here, or excuse me, no u in here, so we're going to multiply by 2 pi. So now we have 8 pi on the outside. And we're going to integrate v with respect to v. We get v squared over 2. And that's 0 to 4. So we end up with 8 pi times 8. So we get 64 pi. So that lines up with the divergence side of it.
Very nice.
Yeah. Okay, so now, let's just talk for a minute about, because I know it's very tempting to parameterize that disk there, u, comma, v, comma, 4. Trying to think about whether we should go through that parameterization, or if you're just comfortable with the idea of, if it's the disk, think polar. We only have 2 minutes, so yeah. So if you have some sort of curved boundary, use polar. Curvy. Let's just talk about it for 1 second. So what if we parameterized it this way? U, comma v, comma 4. So this is our parameterization. Here, notice now when you do your RU, notice that you are in fact going to get, you are going to get the correct normal vector that you sort of think about with a plane. So when you do RU cross RV, you're going to end up with 0, 0, 1, right? 0, 0, 1. So the normal vector works out fine. But what are the limits for your u and your v?
Ugly.
Ugly. So v is going to be, so what is the circle? It's a radius what?
4.
4. So we're going to have, one of these limits is going to go 0 to 4, or minus 4 to 4. Let's just say it's u. And then the other one is going to go from
Negative square root.
negative square root to positive square root. And we're going to have 16 minus u squared inside. So then it's all going to come out in the wash. When you do your integral, when you dot this with your vector field at your parameterization, when we dot u, what was the vector field? The vector field was just the XYZ. So we're going to get u, v, 4 dotted with 0, 0, 1.
This is going to be 4.
Oh, this is goofy because it's just going to pan out super easily. So du dv, this is going to be double integral 4 du dv, and this is going to end up just being the area of the disk, actually. So let me switch the order of integration here. This should be dV to U is better because of the way we did it. V to U, U is negative 4 to 4. This is going to be minus square root to square root. So it's going to end up still just being 4 times the area of the disk. So you actually don't even need to really evaluate it. What's the area of the disk? The radius was 4, so this is going to be 16 pi. So we get 64 pi. So we didn't really have to deal with the nastiness of the limits because we ended up with something that geometrically meant the area of a disk of radius 4. But you can see why it's better to parameterize with the curve in mind.
Because
Go polar.
Yeah, not everything will come out this nicely. And
Yeah, sometimes these will cause a lot of grief if this was not a constant.
Good grief.
yeah, so
Good grief.
the less
and bad
rocks you
grief.
put in the wash, the better. Yeah.
I agree.
A lot